Okay, so we went over one way of calculating delta heat of reaction by using Hess's law and combining reactions in sequence. This is a different way of doing that by using standard enthalpies of formation. So we can actually calculate a heat of reaction from tabulated standard enthalpies of formation. This is, your book's using this analogy of the elevation, and I like that. How do we define zero elevation? Sea level. Why? Why is that zero? Why isn't the center of the Earth zero? Because sea level is more convenient, right? It's convenient. You define zero somewhere and you measure everything relative to that. So we do the same thing with these enthalpy changes. We're looking at the changes. We're not looking at the absolute value of this, what the actual value is. We're looking at changes in value. So we can define zero wherever we want. So we pick a convenient place to define zero. So just like we measure changes in altitude relative to sea level, we measure changes in enthalpy relative to the enthalpies of pure elements in their standard states. So we have definitions for what that is, what a standard state is. So the standard state is the state of a material at a defined set of conditions. So when we're looking at a pure gas, the gas will be at 1 atmosphere. That's its standard state. If we have a pure solid or a pure liquid, that will be in its most stable form at 1 atmosphere of pressure and the temperature of interest, which is usually 25 degrees Celsius, approximately room temperature. If you have a substance that's dissolved in a solvent, then we're going to say the standard state is a concentration of 1 mole per liter. So these are just definitions of the standard states of conditions. Whatever the substance is, if it's at that condition, we say the standard enthalpy is 0. So oxygen gas. Pure oxygen gas at a pressure of 1 atmosphere, we say has an enthalpy of 0. And then we can compare that to other oxygen in other forms, like maybe as part of a water molecule. So the standard enthalpy change is the enthalpy change when all reactants and products are in their standard states. And we put this little degree sign up there to indicate that everything is in its standard state. The standard enthalpy of formation, now we're adding a little F down here. So this is enthalpy of formation. The degree sign tells us it's a standard enthalpy, and the F says formation, is the change for reaction forming 1 mole of a pure compound from its constituent elements. The elements are in their standard states, and a pure element in its standard state is defined to have a formation, enthalpy of formation of 0. So we're saying if you start with elements in their standard states, that's 0, and we build on that. And some things will have a positive enthalpy and some things will have a negative enthalpy. This is an example of a table of standard enthalpies or heats of formation. And you'll notice this, a temperature specified here, 298 Kelvin. That's 25 degrees Celsius. This is a small abbreviated table. There are books like the CRC is a chemical reference book. CRC stands for Chemical Rubber Company. But it has pages and pages and pages of tables like this. So what does this all mean? So here's bromine, the element in its most stable form, which is as a molecule. At 298 K, it's a liquid. Its heat of formation is 0. If we take bromine and we make it into HBr, hydrogen bromide gas, the standard state of that would be at 1 atmosphere of pressure. The enthalpy of formation for that is minus 36.3 kilojoules per mole. So that releases energy. And so these are giving us points of reference, basically. So we're measuring change of enthalpy just like we measure change of elevation relative to this point that we decided on. So we say the standard enthalpies for elements in their stable forms in their standard state is 0. That's like being at sea level. For many compounds, delta H is negative. That's like a negative change in enthalpy. That's like going below sea level. But for some, it's positive, and that's going above sea level. Reactions of elements in their standard state to form 1 mole of a pure compound. That's not actually a sentence, is it? We're going to look at these formation reactions, and we need to use elements in their standard states. If you're not sure what the standard state for an element is, go look in the table and find the form of that element that has delta HF equals 0. So let's go back to that table. So, like bromine. Well, there's 2 possibilities here. Bromine, the atom in the gas state, bromine as a diatomic molecule in the liquid state. Both of those are elemental forms of bromine. How do we know which one is the standard? It's the one with delta HF equals 0. That happens for other things as well. Here we've got chlorine as an atom and chlorine as a molecule. Chlorine as a molecule is the standard state. So that's how you can identify if you're not sure which one you should use.
So there's a standard under these conditions, and then there's a standard state.
The standard state is the most stable form of the element, which is something that you might not know, right? You might not, recognize that it should be Br2 instead of Br. And so by looking at the table, you can see which one it is. The standard states are the same for everything, the standard conditions, 1 atmosphere for a gas, room temperature and 1 atmosphere for liquids and solids, and 1 molar for solutions. When we calculate these for a formation reaction, the definition requires that we form 1 mole of the compound. When you write out a reaction, an equation to form 1 mole, you can end up with fractional coefficients on your reactants. So we're just telling you that's probably going to happen sometimes. So that's just all a bunch of talking. Let's see about putting this together. I think you're going to like this method of calculating heats of reactions better than the one I just showed you before our break. So if we look at this reaction where we've got copper and oxygen forming carbon monoxide, and we want to write the formation reaction. Well, we look at these elements, they have to be in their standard states. And so we look for carbon in the table to find out which is its most stable form. There are several forms of solid carbon, but the one that has a heat of formation of 0 is graphite. And so that's what we have to start with. Graphite is a solid, so we've got carbon, solid in the graphite form. There are other forms. There's buckyballs and there's diamonds. Other forms of elemental carbon, but those are not the standard state. Graphite is. Oxygen, we can't just write O. We need the standard state for oxygen, and that's the diatomic gas. And so these are going to form carbon monoxide. This equation's not balanced, though, is it? We have to balance the equation, But the coefficient on the product, this compound that we're calculating all of this about, this has to be a 0. Not a 0, sorry, a 1. Ugh. This has to be a 1. We're making 1 mole. We're going to calculate the heat of formation that makes 1 mole of the product. In order to do that, we may have to use fractions and coefficients to get the thing to balance out. So 1 carbon and half of an oxygen molecule make 1 carbon monoxide molecule. Bless you. So we can actually look up the heat of formation for carbon dioxide in that table. And it's minus 110.5 kilojoules per mole.
Oh, that's why it has to be minus.
Right, because it's per mole of this. It's per mole of the thing that you're forming. Okay, so here's our example. Write equations for the formation of sodium chloride and lead nitrate from the elements in their standard states. Include the values of the heat of formation for each equation. Well, so here's our, let's do the first one. Our product is sodium chloride. And we have to look at the elements that make this up. So we've got sodium and we've got chlorine. We need to go to the table and look up what these heats of formation are. So I'm just going to go to the page in the book that has this. Hopefully it won't take too long. You're in here somewhere. There it is. So for sodium, we look up sodium in the table. There's 2 elemental forms. Sodium is a solid, sodium is a gas. The one with delta, the heat of formation of 0, is sodium as a solid. So we need to specify this is sodium with a solid. It's a solid. And for chlorine, we look up chlorine in the table. There's chlorine gas as an atom and chlorine gas as the diatomic molecule. The diatomic molecule is the one that has the heat of formation of 0. So I didn't leave much space here, but so the chlorine diatomic molecule is a gas. So I found the elemental states by looking on that table. If you need a table like that on an exam, I'll give it to you. That's not something anybody would want to memorize. Okay? So don't worry about that. Then we have to balance this. This needs to stay 1 mole. And so we're going to put coefficients on the other side in order to make it all balance out. The sodiums are fine, the chlorine's not, so we're going to put a half in here. Then, what's the heat of formation of that? Well, we look up sodium chloride, solid, in the table, and it says minus 411.2. Minus, good grief, minus 411.2. The units are kilojoules per mole. That is the formation equation for sodium chloride solid. Yeah, let me do that over again. It was, the 4 ran into the 1 and looked like another 4. Minus 411.2, yes, 0.2 kilojoules per mole. Any questions about that one? So let's do lead nitrate. So we're just looking at the elements. These are not reactions that would necessarily happen, okay? We're just describing what things are coming together to make this. So lead nitrate, this has three elements in it. Lead, nitrogen, and oxygen. So there's going to be lead, there's going to be nitrogen, there's going to be oxygen. And we're going to end up with lead nitrate. Solid. I'm just going to plan to put the heat of formation down here. So we need standard states for these elements. We look them up in the table. So lead. It's not in there, is it? Well, there's a more extensive table in the back of your textbook. But let's think about lead. Lead's a metal, right? Do metals form diatomic ions or anything crazy like that? No. In what state are most metals at 25 degrees Celsius? Solid. This is going to be lead solid. That's going to be lead's standard state. How about nitrogen? Nitrogen is in the table. That's one of those diatomic elements, and it is a gas at room temperature. So this is N2 gas. And maybe you can predict that oxygen will also be O2 in the gas. Oxygen can be in the form of oxygen or of ozone, O3, but ozone is not the standard state, it's oxygen. So those are the standard states for the elements. And then we balance the equation. And what's a little different is we need to have this be 1. And so we only put coefficients on the left side. It still ends up being balanced though. So we look over here and we've got 2 nitrogens, right? So that one's okay. There's 1 lead, that one's okay. Oxygens, we've got 6 of them. So we need to put a 3 in there. And then we need the heat of formation. And so we are going to have to go back to the back of the book. And Appendix 2 gives all sorts of useful stuff. So we look under lead, and we have lead nitrate, lead 2 nitrate solid, and the heat of formation, standard heat of formation is minus 451.9. Minus 451.9 kilojoules per mole. Any questions?
Is it diatomic? Will it always be in its diatomic form, like the N2O2? Or
Right. The 7 diatomic elements you will find as diatomic molecules in their standard state. And most of them are gases. On the periodic table, the big one in the back is color-coded. Bromine is blue and mercury is blue because at room temperature those are liquids. The black ones are solids at room temperature. So iodine is a solid at room temperature. That's a diatomic molecule, I2 solid. And the red ones are gases at room temperature. So nitrogen, oxygen, fluorine, chlorine, and hydrogen would all be gases at room temperature. Good question. Any other questions? Let's see what's next here. So we can calculate the heat of reaction using these heats of formation. The heat of formation corresponds to the formation of a compound from its constituent elements in their standard states. And we learned how to write those equations and look up the numbers. If we flip that around, the compound going to the elements, we change the sign. And that would be the change in enthalpy for the decomposition of that compound into the elements. And so what we do to calculate heats of reaction is in our minds, we take the compound, take it apart into its elements, and then mentally put it back together into our product compound. So we can write any reaction as the sum of formation reactions, or the reverse of those, for the reactants and the products. I think I want to jump ahead here a minute. Let's look at this one. So here we have the combustion of methane. So methane gas reacting with oxygen to form carbon dioxide and water. So we can calculate an enthalpy change using, like we did before, using a series of equations. And I don't know that anybody here really liked that method that much. Or we can think of it in terms of heats of formation and the elements. And so mentally what we do is we take methane and we decompose it into its elements. And we can look, we just learned how to write this formation reaction for methane. And we can look up the heat of formation. These are always written as forming something. So the elements in their standard states forming 1 mole of this, we can look up the heat of formation in a table. This is one of our reactants. So this would be reversed in sign because we're decomposing this, we're decomposing oxygen, but that's already in its standard state, so that one's 0. Then we're forming CO2. Here's the formation reaction for CO2 and its heat of formation. And we're forming water. So mentally what we're doing here, here's our reactants. We're taking the methane and we're decomposing it into graphite, hydrogen, and oxygen. The heat of formation for methane is minus 74.6. The heat of decomposition would be the opposite. We're going the opposite way. So this is plus 74.6. And then from elements in their standard states, we're forming CO2, which is minus 393.5 kilojoules, and we're forming water. Okay, so it's like, if these are little Lego creations, we're taking them apart into their individual blocks. And we're figuring out, okay, how much energy was involved in that, and now we're going to put them back together into these new compounds, and how much energy is formed in that. Sometimes it's released, sometimes it's absorbed, but we just add them all up. This process does not happen during this reaction. It doesn't. This is a mental exercise that we've developed so we can calculate what these reaction heats of formation, or the heats of formation are. So we could take these reactions and add them together and multiply and stuff like we did before. But we don't really want to do that, do we? Or we can use this concept here. The standard enthalpy for the reaction is equal to the products minus the reactants. This is the same idea, delta being final minus initial. The products minus the reactants. This large Greek sigma means sum. And so we take the sum of the heats of reaction for all of the products, and this is the coefficient. We have to remember the coefficients. It's the sum of all of the stuff for the products minus the sum of everything for the reactants. So that being said, let's do an example. Back to those chemical hand warmers. They produce heat when they're removed from their airtight plastic wrappers, because then oxygen gets into the iron filings. And so here's the reaction. 4Fe plus 3O2 is giving us Fe2O3. Calculate the standard heat of reaction for this reaction and calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. So we can do this using heats of formation. So the standard heat of reaction is going to be the heats of formation for the products minus the heats of formation for the reactants. So here we have a product, Fe2O3. We're going to go to our table. Here you're going to have to use the one in the back of the book. And we're going to look this up. And this is iron. Where's iron? There's iron. Okay, so for Fe2O3, solid, the standard heat of formation is minus 824.2. So minus 824.2, and the unit on that is kilojoules per mole. We have to multiply, oops, not that one. We have to multiply, got lost here. So multiply by 2. Because remember, enthalpy is an extrinsic property. It depends on how much there is. And this is telling us there's 2 of those. So we need to multiply this by 2. That's the product. Then we subtract the sum of all the heats of formation for the reactants. Well, iron. If we go look that up, we see Fe in the solid state. That's its standard form. So that one's 0. And yeah, we should multiply it by 4. Still 0. O2 in the gas state, that's also its standard state. And so that is 0. So for this reaction, we've got 824.2 times 2, and it's negative 164.8.4 kilojoules per mole. I think what we're really supposed to do is, this is 2 moles, and the moles cancel out. And so this ends up just being kilojoules. But it's kilojoules for as the reaction is written. Delta H standard AHxn minus 1648.4 kilojoules. This applies to this particular equation. So this much is generated when 4 moles of iron react with 3 moles of oxygen and form 2 moles of the oxide. Did that make sense? That's easier, isn't it? I'm not sure. I think maybe they do the other one so that when we get to this one, you're kind of relieved. Like, oh, phew, that's better. Now, this is asking how much heat from a hand warmer containing 15 grams of iron powder. Okay, so hopefully this part will seem familiar and perhaps easy in comparison. 15 grams of iron, we could figure out how many moles of iron, right? Using the molar mass of iron. And then 4 moles of iron would make that much energy. So 15.0 grams of iron is 55.85. Moles of iron up here, 55.85 grams of iron down there. The grams cancel out. And then we know that there's minus 1648.4 kilojoules per 4 moles of iron. Delta H pertains to this equation with molar amounts for the coefficients. So because this is 4 moles of iron, I've got this much energy for every 4 moles of iron. And so this ends up being minus 442.72 kilojoules. 15 grams has 3 sig figs, so we should round this to minus 443 kilojoules. Now when we say how much heat is produced, 443 kilojoules. The sign is there. The sign tells us the energy is being released, but when we talk about it, we would say 443 kilojoules are produced, and the sign is in the produced. If it was positive, we'd say 443 kilojoules were absorbed or used or something. Any questions? Yes?
I think you multiplied by 4.
Yeah.
Oh, I probably did. Let me try that again. Actually, I think I maybe forgot to divide by 4. I maybe forgot the 4 was there.
Yeah, that's it.
Yeah, thank you. Okay, let's try that again. Minus 111. Is that better? Thank you. Any other questions?